So in this video, we're going to look at calculating the volume of revolution using the disk method when two integrals are needed. So in this example, it says consider the region R bounded by the graphs of f of x equals x squared plus 1, y equals 0, x equals 0, and x equal 1. Find the volume of the solid formed by revolving the region R about the y-axis, so a y-axis revolution. So the bounded region, x squared plus 1, is the parabola. X equals 0 is going to be on the y-axis. X equal 1 is going to be a vertical line here. And y equals 0 is going to close us up along the bottom. So this is the region that we want to revolve about the x-axis. And what we want to see is that there's two separate things going on. There's right at the vertex of the parabola here, if I dash in a perpendicular line to the line x equal 1, I can see that how I have to calculate the volume of revolution here, call that region 1, is different than how I need to calculate the volume of revolution here. In fact, we, for this region, can just use the vertical axis of revolution formula that we developed in video number 1, whereas this one from here, this region here, if we revolve it around the x-axis, this piece here is going to be missing. So we have a washer method being needed for the second piece. So this really needs to be broken into two separate pieces. And I'm going to do this in two PowerPoint slides. I'm going to look at this two different ways. So the first way, I'm going to be very mechanical about it, just employing the formulas that we see here. And then I'm going to do it again a little bit differently, making use of basic geometry. So for this one, I want to recognize that from 0 to 1, I have a radius of revolution being controlled by a characteristic rectangle that looks like this. And that's all the way up through y equal to 1. So I have dy slices right here. My radii are x's because I have a horizontal representative rectangle. My radii are x's, but in this case, x is always equal to 1. So to get the volume of revolution for this first region, I would simply take the volume equals pi. I'm going to run it. I have dy slices, so I'm going to go from 0 to 1 on the parabola. I can get that 1 right there by just plugging 0 into the parabola and finding out that the vertex is at 1. So I'm going to go pi times the radius squared, but the radius is 1. And then I'm going to multiply by the width, which is dy. So pi r squared h, but h is dy. And then I'm going to add on to that the volume of the region I get when I revolve this around the y-axis. And what I want to recognize here is I have a washer method with this piece missing. So starting here and running through here, I'm going to use my washer method. I'm going to say, hey, I'm going to take pi times, I need the large radius, but the large radius, the representative rectangle, is still going to be all the way out to the line x equal 1. So the outer radius is going to be 1 squared, and then it's going to be minus, and then I need that inner radius, and my representative rectangle for the inner radius is going to be sitting right here, and the parabola is controlling the inner radius. So my radii, because I'm oriented horizontally, are x's, but I need x as a function of y. So to do that, I'm going to grab my parabola. I have the parabola y equals x squared plus 1, and we need to solve it for x. So we're going to get y minus 1 is x squared, and then we're going to take the square root of both sides. To get the square root of y minus 1 is the radius x. And I don't need the negative square root again because I'm ignoring that half of that parabola. So it's going to be, from the washer method, the large radius squared, which is 1, minus the square of the smaller radius, which is the y minus 1 quantity squared, multiplied by not dx in this case because our slices are dy slices. So I'm going to be multiplying by dy. So the washer method, we developed it with respect to the x-axis, but recognize that the concepts are the same for the y-axis. We just do things with respect to that axis instead. And now I could go through and calculate this. I'm going to go pi. When we integrate 1 dy, we're going to get y from 0 to 1 plus pi. I need to simplify this a little bit, so I get 1 minus parentheses. I square the square root, I get y minus 1 falling out dy. I can simplify this. So this equals, this is going to be pi times 1 minus 0. There's a tough calculation, plus pi times the integral. This should be the integral. I didn't put my limits of integration. This is running from 1 to 2. So this is going to run from 1 to 2, from 1 to 2, from 1 to 2. And I get 1 minus y minus minus is going to be plus 1. So I get 2 minus y dy. And now that's ready to integrate. From here, I get just pi plus pi times the antiderivative of 2 with respect to y is twice y minus antiderivative of y dy is going to be 1/2 y squared from 1 to 2. Now you've got to plug those limits of integration in, so we get pi plus pi times, we're going to get 2 times 2 minus 1/2 of 2 squared minus parentheses, plug in a 1, we get 2 times 1 is 2, minus 1/2 y squared is just minus 1/2. And now we just need to keep simplifying. Pi plus pi times 4 minus 1/2 of 4 is 2 minus 2 plus 1/2. And from there we get 4 minus 2 minus 2 is 0 plus 1/2 is just 1/2. So we get pi plus 1/2 of pi is going to be 3/2 of a pi for a volume. So this was just kind of mechanically applying the different formulas that have come up in this section. But notice we could take a little different approach to this. I could say, hey, I want to find the area, the volume I get when I rotate this region around the y-axis. So what I could do initially is just ignore the parabola. I could say, well, what volume do I get if I rotate this region around the y-axis? Well, if I rotate this rectangle around the y-axis, I just get a cylinder. I get a cylinder of radius 1 and height 2, and I know how to calculate the volume of a cylinder. So I could say, well, my volume is going to be equal to, what's the volume of a cylinder? Well, it's pi times radius squared times height. Radius is 1, height is 2. My cylinder looks like this when I spin it out. Radius 1, height 2, oriented on the y-axis. So there's that. And then I could say, well, when I rotate this, I want to lose this region right here. I want this region here. I don't want that. I want that subtracted off. So I'm going to subtract that. Okay, so what's the volume of that region? Well, that is going to be, hey, here's my representative rectangle. Those are dy slices. My radii are going to be x coordinates because I'm oriented horizontally. Solve that parabola for x. So I have y equals x squared plus 1. We get y minus 1 equals x squared. We get the square root of y minus 1 equals x. So subtract pi times the square of the radius times this width dy to get our cylinder volume, and then run that from 1 to 2. And this right here, what are we going to get? We're going to get 2 pi coming out of that, minus pi times the integral from 1 to 2 of y minus 1 dy. And now grind away at it. 2 pi minus pi times 1/2 y squared minus y from 1 to 2. And just pop in pieces and go. So 2 pi minus pi times 1/2. 2 squared is 4. A half of 4 is 2 minus, plug in a 2, minus 2 minus parentheses. Plug in a 1, we get 1/2. Minus, plug in a 1, we get 1. And keep pounding. 2 pi minus pi times 2 minus 2 is 0. 0 minus 1/2 minus minus plus 1 is going to be a half equals 2 minus a half times the pi is just going to be 3/2 of a pi. And if we haven't made a mistake, that should match what we got on the previous slide. So the idea here is we can be very mechanical with these volumes of revolution, or we can kind of think through the geometry of what's going on and see if there are ways to simplify our calculations and not be so reliant on formulas.